Parametric test. So what's a parametric test? It's a test that one makes assumptions about the parameters, as in the defining properties of the population distribution from which one's data is drawn. So in these tests, inferences are based on the assumptions that we make about the nature of the population distribution itself. And these tests are always used for normal data, as in normally distributed data. And what are the types of parametric tests? Well, there are three primary types. There's z-test and t-test, and then there's ANOVAs, which stands for analysis of variance. Now we use z-test and t-test to look at true population means and proportions, compare those against one another and test those. ANOVAs looks at multiple population means at the same time and test if there's significant differences amongst those groups. First, we'll cover a z-test. So a d-test is performed where the test statistic t, the standard deviation is known, the population is normal, and the sample size has at least 30 people, 30 individuals, 30 things, whatever we're measuring. Now the formula to calculate the z-statistic is z equals the sample mean minus the population mean divided by the standard deviation over the square root of the sample size. So let's see what this actually looks like in practice. Let's say that the test scores of an entrance exam fit a normal distribution. The mean test score is 72. The standard deviation is 15.2. So let's compute the percentage of students scoring an 84 or more. We'll use p-norm, which is a probability normal distribution function, to find the required percentage of students in the upper tail of the normal distribution, since we're looking to achieve a score and identify the proportion of students with a score greater than 84. So in the formula, we have p-norm 84, the mean of 72, the standard deviation of 15.2. We also have this aspect where we can control the lower tail equal to true or false. So we can set it to true if we want to find the probability of values no larger than z. We set it equal to false if we want the probability of values z or larger. In this case, we're setting it to false because we're trying to look for above that 84 threshold. We get 0.21494. Now there's a probability. So what that means is 21.49 or 21.5% of the population is likely to score an 84 or more. Now because it's probabilistic, that also means that 100 minus 21.5 or 78.5% of students are going to score below an 84. So a t-test will be performed when the standard deviation is unknown, the sample standard deviation is known, and the population is normal or normally distributed. So to calculate t, it looks very similar to z. We have t equals the mean of the sample minus the population mean divided by the standard deviation of the sample over the square root of the sample number. So let's say we wanted to find out the 2.5th and 97.5th percentiles of a student's t-distribution with 5 degrees of freedom. Now, degrees of freedom refers to the test statistic in regards to how many objects can vary freely. So various items can affect the degrees of freedom, including the number of variables in a model, the number of groups in a model, and a handful of other things. Often, we'll have different degrees of freedom. And for samples versus population, we'd use n minus 1. So if we use the quantile function qt against these decimal values with 5 degrees of freedom, we get negative 2.57 and 2.57. That's that 2.5 and 97.5 percentiles. And there's your t-scores. Lastly, we'll cover ANOVA. So while z-test and t-test compare two different groups and try to see if there's significant differences between those two groups, ANOVAs will look at multiple group comparisons to see if there's significant differences between and across all groups. For example, perhaps an environmentalist wants to know if the average amount of pollution varies in several bodies of water. So let's say that environmentalists collected samples of water from 40 different lakes across the United States. Well, we can't use a z-test or t-test because there's 40 of them. And we need to just compare, we can't just compare two. So comparing those 40, we use an ANOVA. Same thing, if a sociologist wanted to find out if a person's income varies according to his or her upbringing. We might have multiple groups for different upbringings, and then we want to compare and see if there's significant differences according to the person's income in those different groups. Now there are two types of ANOVAs. There's one-way and two-way ANOVAs. So if we look at a one-way ANOVA, it uses the variance to determine if a statistically significant difference exists among several group means or not. So what our null hypothesis says is that the group mean for each group is equal to one another. And for a one-way ANOVA, the ratio of the between group variability to within group variability follows an F distribution when the null hypothesis is true. And we'll talk about an F distribution. Now there's a few types of assumptions for parametric tests that are required. All samples have to be random and independent. If we had lakes that were bleeding into one another, then we wouldn't be able to ascertain whether there's significant differences in those two lakes because those lakes might be influencing one another in regards to their pollution. Number two, each population must be normal. We can't have biased populations or erroneous type of populations. The factor has to be categorical. It can't be numeric, integer, continuous. We have to have some sort of grouping. The populations need to have equal standard deviations. If we were trying to compare mean incomes in different cities, well, the standard deviations may vary drastically between, say, San Francisco and a small town in Idaho. And the result has to be numerical so we can statistically compare those differences. So, let's find out if there's a difference in the mean grades among sororities, assuming the mean of the four groups, mu1, 2, 3, and 4, the population means of the sororities. So our null hypothesis says sorority 1, mu1, is equal to sorority 2, mu2, is equal to sorority 3, mu3, is equal to sorority 4, mu4. Now, not all of the means of mu1, 2, 3, and 4 are equal is our alternative hypothesis. It doesn't mean they all have to be significantly different from one another, but at least one of those means has to be different. Now, we also have to calculate the degrees of freedom. So for our numerator, the degrees of freedom is the number of groups minus 1. There's 4 groups, minus 1 equals 3. The denominator says it's n minus k. So n is the sample size, 20, minus 4 groups is 16. So our test statistic cutoff is an F value of 2.23. And so when we calculate the probability, we have 0.1241. Now if we set Cronbach's alpha at 0.05, if we set at 0.01. In either case, the p-value, 0.1241, is greater than alpha. So it doesn't fall outside of that rejection range, so we cannot reject the null hypothesis. So without sufficient evidence, based on our test, we can't conclude there's a difference among the mean grades for these 4 sorority groups. Let's take another example. A fast food chain wants to test and market 3 of its new menu items to analyze if they're all equally popular. So we took 18 random restaurants for this study, and we randomly assigned 6 of the restaurants to test market the first menu item, randomly assigned another 6 to test the second item, and the remaining 6 to test the third item. Now the table shows the sales figures of the menu items in the 18 restaurants. So the question is, at a 0.05 level of significance, let's test whether the mean sales volumes for these menu items are equal. Now, I'm going to recommend that you pause on each of these pages to complete each of these steps, and then you can re-enable the play button once you've done each step. So, first, why don't you copy and paste the sales figures in the table, this table right here, and label the text file fastfood-1.txt using the text editor, Notepad, Vim, Emacs, whatever you use. And now open RR Studio, load the file into a data frame called df1 using the read.table function. The syntax here will be df1 equals read.table, fastfood-1.txt, and we want header to equal true. Now, in R, once you've done that, type in df1 and make sure the following code shows up as the output below. Now, From that matrix, let's concatenate the data rows into a single vector labeled R. So using the syntax, you should get an output that instead of a matrix, you'll get a single vector, numeric string. And what you want to do now is assign new variables for the treatment levels and number of observations. So we can have f equals concatenate items 1, 2, and 3. We specify that k equals 3, and we specify that n equals 6, because that's the number of treatment levels. We have 3 different food types, 3 items, and we have 6 restaurants within each of these. Now, create a vector of treatment factors corresponding to each element of R in step 3 using the GL function. So, as you go through these steps, we'll finally get to the point where you can apply the analysis of variance and ANOVA. And you can see that as AV equals AOV R tilde TM. The tilde is usually next to the 1 using the shift key. And print out that ANOVA table with the summary function. Summary on what you labeled AV. And what you'll get is this output file. And you'll see df equals 2, so that's the degrees of freedom. You have sum of squares, mean of squares, the f value, and the probability. So you don't need to care as much about those first 3, and you don't need to care as much right now about residuals. The 2 prominent things to focus on are the f value and that p value, that probability. So the f value shows a 2.54 and a probability of 0.11. Well, what does that mean? If you recall from our earlier work, that 0.11 is greater than 0.05, which means we fail to reject the null hypothesis. And that means that the mean sales volumes of all these new menu items are equal. Does that make sense? Perfect. Then we'll move on. The F distribution, also known as the Fisher-Schneider distribution, is a continuous probability distribution that arises frequently as the null distribution of a test statistic, most notably in ANOVAs. And one of the important things to know is the F ratio, and that's a value derived from 2 estimates of the variance below. It's based on the sum of squares between samples and the sum of squares within samples. So when we're looking at the variance between samples, it's an estimate of the variance of the sample means where the sample sizes are the same. And when these sizes are different, the variance is weighted to account for the different sample sizes. And the variance within samples is an estimate of the variance, the average of the sample variances. So when the sizes are different, the variance within sample is weighted. So thinking of this cognitively, let's take it from a humanistic-based approach. So variance within sample. If every day I go to work at 8 a.m., Monday through Friday, and then next Tuesday I show up at 11 a.m., that's different, right? That's not unique to who I am because I always show up at work at 8 a.m. So the variance within the sample is that I had a difference there. Now the variance between would look at me versus my coworkers. So if I show up at 8 a.m. every day and my coworkers show up at 8 a.m. every day, there's no variance between the samples, between us as different individuals or as groups. But if I show up or my team shows up at 8 a.m. every day, and other coworkers or other teams show up at 1 p.m. every day, then that's a variance between the sample groups. There's significantly different times that we show up. That's the difference between sum of squares within and between. Now, a two-way ANOVA refers to a hypothesis test where the classification of data is based on 2 independent variables. So for example, a company could base its sales classification by identifying the sales by a salesman and sales by a region. Now, when we're looking at these parametric tests, there's samples here, or assumptions here. The first assumption is, again, the normal distribution of the population sample. We assume that that sample is a normal bell curve. Number 2, measurement of dependent variables are continuous. Number 3, that the categorical independent groups have the same size. We can't compare a group with 20 individuals to another group with 3,000 individuals. Number 4, independence of observations. So these groups have to be independent. And lastly, we have to have homogeneity of the variance of the population, meaning the variances have to reflect it.